Okay. For a reaction where we have reactant A and reactant B, and the small letter A and small letter B represent the coefficients. Actually, I think it should be, oh no, that's right, that's right. The rate of the chemical equation generally increases as reactant concentration increases. Does that make sense with what you've learned so far? Yes. However, different substances, depending on how they behave in the reaction, can increase the rate in different ways. Okay? So rate is proportional to A to the M, so the concentration of substance A to the power of M, and B to the N. So rate is proportional to concentration of A raised to some power. Could be 0, 1, 2, whatever. It's B raised to the N. But what you'll notice is that this right here is not little a. It's not the coefficient. It's tempting to want it to be the coefficient, but it's not. Okay? And N is not B. The only way that we can figure out the exponents is to do experiments. Okay? So M and N, those exponents, are determined experimentally. Actually, it's not the only way, but it's one of the only ways. So for any equation, for any reaction, we call it the rate law equation. Rate is equal to K. What does K stand for? K is a constant. It's specific to the reaction and the temperature, okay? Times the concentration of A to some exponent, so reactant A times reactant B to some exponent. So if you increase concentration of A, the rate will increase. If you increase the concentration of B, then the rate will increase, unless your exponent is 0, which means that probably that particular reactant is coming in after the rate determining step in a mechanism. Okay, because otherwise, like, how could you increase the concentration and not have it affect the rate? Okay, but that's where that comes in. So the rate constant varies with temperature, but if you keep your conditions constant, it is constant. Exponents M and N, again, they are constant with temperature. They can only be determined experimentally. They are not the coefficients. So that's just a little summary table. Oh, and look, I thought it was so important I put it in a box with stars in it. The exponents M or N can only be determined through experimentation. They may or may not be the values of the coefficient. If they do match the coefficients, that is just a coincidence. Alvin. Oh, we'll take a look at that in a second. Okay, we'll get to all the units. Yeah. It works out because K will have units that cancel everything out, so that rate is equal to change in molarity over change in time, usually. Okay. Exponent values are usually 1, 2, 0, 1, or 2, but they can be 3, and in some cases they can even be fractions. Okay. We're usually going to look at only values of 0, 1, or 2, at least for now. Later on, we might see some fractions. the value of exponents are going to determine what we call the order of the reaction. We'll get to that in just a moment, the order of the reaction. So, if a reaction has a single reactant and the value of the exponent is 1, it is said to be first order. Okay, 1, first order. Okay? If we only had one reactant, if we had reactant A and the exponent was 2, what order would we say it is? Second order. This part's easy, right? Doesn't necessarily make a lot of sense, but it's easy. Yeah? Uh-huh. Oh, something breaks down. Yeah? Yeah. If more than one reactant is present in a reaction, the sum of the exponents, m and n, is called the overall reaction order. Yes? 0, you can have 0, and that would be called 0th order. So if the exponent is 0, it's called 0th order. So if we have a reaction where the rate is proportional to A to the power of 1 and B to the power of 2, we can say that it is first order with respect to A. Okay? We can say that it is second order with respect to B. And then if we look for the overall order of the reaction, it is just, we add up the exponents and we say we've got a 1 with respect to A, a 2 with respect to B. Overall, it is third order. Okay, yes? No, you have to figure it out by doing an experiment. Okay, yeah. So here we have reaction number 1. Experimentally, somebody did some experiments, and don't worry, we'll get to what kind of experiments soon, so it'll make a little more sense. Experimentally, the rate was found to be first order for N2O5. That means that the rate varies directly with N2O5. In other words, the rate is proportional to N concentration of N2O5. And we can write the rate law. All you have to do is write rate equals. You need the rate equals. And then you write K, because a rate law needs a K. And then you say times N2O5 to the power of 1. You can leave off the power of 1 if you want to, obviously, because it's just the same, okay? You can leave off the 1. Yes? You'll be told or you'll be given experimental results that will allow you to determine it, and we'll get to that, okay? Now, let's look. There's a 2 in front of the N2O5. Is that the exponent? No, okay? What is the overall reaction order for this reaction? First, because there's nothing else there. Okay, so it's first order with respect to N2O5. It's also first order overall because that's the only thing that is there. Okay. Here's reaction number 2. It was found to be second order for NO2 and 0 order for CO. So if we write our rate law, what that means is that if it's second order for NO2, that means that rate varies with, is proportional to concentration of NO2 to the what? To the 2. And if it's 0 order for CO, that means that rate is proportional to concentration of CO to the 0. So we can then write our rate law, and remember it involves us writing rate equals, and then K, and then we put in our 2 concentrations raised to their appropriate powers. And of course, anything raised to the 0 is just 1, so you can simplify this down to rate equals K NO2 squared. Okay. Overall reaction order is 2. Reaction 3. Experimentally, the rate was found to be second order with respect to HI. That means that rate is proportional to what? Concentration of HI to the power of 2. When we write our rate law, don't forget to write rate equals and K constant, and then you would put in your concentration. So you need to have all those 3 things, okay? This should say HI. Okay. So you guys are going to try these little exercises here. Try writing the rate law, and then you're going to determine the overall reaction order. And I know in the past I've had problems with some of my answer keys, so we'll see if I've managed to fix it. You guys are going to check my answer key for me. Yes. Yeah, because C to the 0 is 1. So yeah, no, not in the rate expression because it's irrelevant. But you can also get rid of it. Yes. By the way, if anyone wants to take balloons today at the end of class, please do so. Okay. But no playing with them in other people's classrooms, because that'll get in trouble. Sherry just caught another mistake. I copied and pasted the whole thing. In addition to this being HI, this should say second order. Okay. Now, did I get my answers correct? Are you finding any that I did wrong? Oh, and I didn't write number 6. I just left it out, apparently. Oh no, I missed, which one did I miss? I missed number 4. I missed number 4. Okay, so number 4 is actually this is 5 and 6, right? Yeah, okay. How did I do on the ones that I wrote answers for? Did I get them correct? Yes? Shall we do number 4 together just to make sure we have an answer for it? Okay, number 4. The rate law would be, what would we start with? Rate, and then equals K, concentration, NO2. And you don't have to put the 1, you can put the 1, but you don't have to. And Cl2, again to the 1. What's the overall reaction order? 2. Beautiful. Yes? Yeah, it'll know moles per liter. Yeah. Yes. Yeah. So we're going to do some stuff here. Okay. So if you are interested, this is BLB section 14.2. So if you're into reading that, you can either sign out a BLB or you can read it. We've got it online as well, okay? That's our big black textbook. For anyone who wasn't with us last year, there's a reason we don't often send them out, because they are big and heavy, and we have an online copy. But if you do want to sign one out, let me know, okay? Like we do have some. Okay, 1.6b, page 4. There are 2 methods that we're going to look at, and the first one, this is the one we're doing here, is the method of initial rates. So we will be looking at the rate at the very start of a reaction. You know how sometimes rate decreases over time, right? Because your concentrations drop over time. So we're going to look at just that very first few seconds of the reaction, okay? So that's what we'll be looking at on this one, and then later on we're going to look at the graphical method, but that's not today, okay? All right, method 1, determining rate exponents using initial rates of reaction. If you increase the concentration of A, the initial concentration of A, and you'll notice I've called that A with a little 0 at the bottom. I've actually made it a little 0 with a strike through because we've been using exponents as zeros just to avoid confusion. However, I've only done that for this one, and then from here on in, I'm just putting a 0 at the bottom. Yes, are we good with that? Because we know that it's not an exponent because it's at the bottom. That little bit thing there stands for, now I don't know which spelling of not it is. I think it's the OU, not. So that is concentration of A, not, which means initial. Don't know why they don't just use an I, but they don't. They use the little not. It's kind of like it means at time 0. Does that make sense? At time 0. If you increase the initial concentration of A and the rate does not change, what would the exponent be? It would be a 0. Yes? So if you increase the concentration of A and you measure the initial rate and you compare it with a lower concentration of A and there is no change, then you have a 0th order reaction, okay? Because concentration of A then just becomes 1, and so it's not changing. If you increase A naught and the rate increases, then the concentration of A will be in the rate equation. It's either going to be A to the power of 1 or A to the power of 2 or whatever. So we're going to have a non-zero M value. So if we increase A, rate will increase. I don't know why I thought it would be confusing to use A naught. I think it's because I was typing the worksheets on the same day, whatever. Just ignore that little note at the bottom, it's just silly. How can we tell if the reaction is first order or second order? So we look at the factor by which we change A naught. Okay, so we do one experiment where we have a concentration of A naught is 1 molar. And then we do a second experiment and the concentration of the initial concentration of A is 2 molar. So what have we done to the concentration? First experiment was 1 molar, second experiment was 2 molar. What did we do? We doubled it. So we have to ask ourselves, what did we do to the concentration of A? Did we double it? Did we triple it? Did we half it? Then we look at what happens to the rate in response to that. When we doubled it, did the rate double? Or did it quadruple? Or did it change by some other factor? So far, so good? Okay. So if we double A naught, that will give us, and if we double A naught, I guess I should say if here, if we double A naught and the rate doubles, what is the exponent for A? If I double A and the rate doubles, yes, 1. Is that fairly obvious? Because if I take this and it was initially 1 and then I change it to 2, the rate will be twice as much. Yes? Okay. So if they change by the same factor, that's going to be a direct relationship, and you're going to have first order with respect to whatever that substance is. Okay? Can you predict what would happen if it were second order with respect to A? What would happen to the rate if we double the concentration? It would quadruple because it goes as the square. And if we tripled it, it would okay, if we double A naught and it quadruples, that means that we have the rate. So if A naught we multiply by 4 and we get rate times 4, A naught times 2, if it gives us rate times 4, in other words, that's rate times 2 squared, and that means it goes as the square. That means it's second order with respect to A. If we double A, initial concentration, and we get the rate times 8. 8 is 2 to the power of 3, so this would be rate varying with the cube of 3, so it would be third order with respect to A. That would be a very unusual situation. We don't get third order very often. Why would we not get third order very often? Yes? Possibly, but also has to do with collisions. Yes? What it would mean is that, like, if you have A collides with A, that would, and it depends on the concentration of A, and it depends on the concentration of A, it depends on A squared, right? Then you could be like, oh, well, but if it's A cubed, that means you have to have 3 collisions now, all at the same time kind of thing. I think I'm getting off on track here. Forget I said anything there. If you double the rate will octuple, because I can't apparently type. There we go. I don't know if that's the correct, it'll times by 8. So here's just a little chart to summarize it. When the initial rate is doubled, when the concentration is doubled and the rate remains unchanged, you have a 0th order reaction. When you double the concentration and the rate doubles, you have a 1st order. When you double the concentration and the rate quadruples, you have 2nd order. Okay? Let's take a look at something else. What if we have the initial concentration is tripled? If I triple it and the rate remains unchanged, that would be what order? 0th. If I triple initial concentration and the rate triples, that would be 1st order, because if it does the same thing as the concentration, that's 1st order. If I triple it and the rate goes up by a factor of 9, that would be 2nd order, because 9, of course, is 3 squared. Yeah? And if I half the concentration, and it doesn't change, that's 0th. If I half the concentration and the rate gets halved, that's 1st order. And if I half the concentration, the rate goes to 1/4 or 1/2 squared, that's going to be 2nd order. All right, so we are usually given some data tables, and they look a lot like this. What is the order of this reaction with respect to A, and what is the rate law for this reaction? Do you think you could do that? So basically you look and you say, what have I done here between experiment 1 and experiment 2? What have I done to the concentration? I've doubled it. And within the same, like when I go from experiment 1 to experiment 2, what happened to the rate? It also doubled. You can do the calculation on your calculator if you can't see it. You can go 9.6 divided by 4.8 and you'll get 2. You could check this by looking at 1 and 3, but you really don't have to. Once you've determined it with one set of experiments, you don't need to do it, but you could. Let's say you wanted to compare experiment 1 to experiment 3. We triple the concentration. What happens to the initial rate? It triples. So what is the order with respect to A? 1st order. Please write the rate law for the reaction. Rate equals K concentration of A, or rate equals K concentration of A to the 1. Yes? Wouldn't you be able to figure out the value of K? Could you figure out the value of K? You're just getting ahead of yourself. Yeah, absolutely you can. So you would, in order to figure out the value of K, what would you do? Oh, yeah, sorry, go ahead. Oh, it would be outside. That's just me being silly. Thank you. Yep, always good. That's why I have all my proofreaders here, right? You can just solve the equation and use one of the data points. Shall we do it? Shall we solve for K? We're going to get the units and the value of K. What's K equal to? K is equal to rate divided by concentration of A. Where could we get values for rate and concentration of A? You pick an experiment. Doesn't matter which one, you'll get the same result no matter what. So let's pick experiment 1 because I like working with things that have like a 1 in them. That makes me happy. It means the math will be easier. So we have 4.8 times 10 to the negative 6. And I have to be honest with you, when I do the math, I like to write molarity as molar because it's less, there's less things. You know what I mean? Moles per liter is just more words and more wordy. So I like to write molar per second. Molar per second. You can write moles per liter per second, but I find this just makes my life easier. Divide by concentration of A, which is 0.01. And what's the unit for the concentration of A? Molar, right? And it will tell you when you have these tables, you'll be given, like, I mean, you should know what the unit of concentration is, but you'll also be given the initial rate. Usually it's molar per second, but it could be molar per minute. You could also, if it was a gaseous system, have a pressure per minute, so it could be atmospheres per minute, okay? But that's just going to affect the unit of K. So what do we get here? We get 4.8 times 10 to the negative 4 molar cancel. So now in our units here we have 1 over seconds. How would we most likely want to write that? Seconds to the negative 1. You could write it as 1 over seconds, but seconds to the negative 1 is probably how you'll most often see it. Okay, so that's the constant, as long as you're at the same temperature. And because it's a constant, you will get that same value if you use the first set of data from experiment 1, or if you use the second data from experiment 2, or the third data, the set of data from experiment 3. You'll get that same number. So one of the things that they'll often do, if they're going to ask a question like this, sometimes you never get, sometimes on an exam you don't get a rate question. Like AP, you never know. Some years you get this, some years you get that. You got to know it all, okay? They want you to be able to find the unit of the rate constant. Well, you just solve for K and put in the units and solve it, and it will sort itself out, and you'll find your units. Yes? Okay. Bloody, bloody, blah. Ooh, look, we have 2 reactants now on our next page. We're skipping this because this was just the answer. Yes, Alvin. Pardon me? No. It will change depending on the order. So for a first order reaction, it's always seconds to the negative 1. For 0th order, it's always molar per second. And for second order, I think it's always molar negative 1, second negative 1. But you can always figure it out. You can memorize them, but you can always figure it out. Yes. Yeah. Like there's no great need to memorize it. I have, just because I was putting these together this summer and I was thinking about like how to go through the process of doing that, but anyway. All right, we have two reactants now. We have A and we have B. Which two experiments could you look at to determine the order with respect to A? Tell your partner, I want to determine the order with respect to A. Which two experiments should I be looking at? Which ones? 1 and 2. Because we are changing A, but what else is happening that's important? B is staying the same. It needs to stay the same. Sometimes you'll get like 5 experiments and you have to pick which ones, and sometimes B is changing. You want to make sure you're not changing both. Okay? So, could you figure out the order with respect to A, please? Oh, we don't want that, do we? Which two experiments should I look at for the order with respect to B? 1 and 3. I don't know why I was looking at 2. There we go. 1 and 3, not 2 and 3. What happens to B between 1 and 3? Well, the B doubles, but the rate, nothing, nada. And so the order with respect to B is 0. So our rate equation would then be K times the concentration of A. Okay? What would the unit be for K? Seconds to the -1. I'm just throwing that out there because we just did it. We just did a first order. Like I said, you don't have to memorize it. All right, there's the answer for that one. We did that already. This is just finding the value and unit of K, and we already did this. Yes, we've already done that. A note on the unit of rate. Rate is always molar per unit time, at least in these ones. It could also be atmospheres per unit time if we're dealing in pressures, but most often it's molar per unit time. But I want you to remember, we can write this all sorts of different ways, so don't be surprised if you see molar per second. Or if you see molar to the times seconds to the -1. Or if you see mole per liter per second. Or if you see bracket mole per liter per second. Or if you see mole per liter times second to the -1. Yes? Yeah, yeah. You could have mole liter to the -1, second to the -1, or you could have mole over liter times second. And those all mean the same thing, and you just need to be okay with like them writing things different ways depending on who's writing it. Yes? Yeah, sure. You might be asked to rewrite the rate law, including the value and unit of K, in which case just solve for K and plug in where K is, okay? How about you guys try example 3 for fun? Because that looks like fun. There's part A, B, C, D, E, F, G. Call me over if you get stuck. Anybody have any questions? We're still working on it? Okay, cool. Did I do something wrong? It's possible. Okay. Yeah. Yes, I think I did something wrong. Let me see. Oh, no, I didn't. I'm good. Okay. Huh? Yes.
Sounds like you said you got to do it. Like, did you calculate it? Okay, because she said it's 0.
Yeah, I've done something wrong. Just at the very end, I think for part G. Yeah. I got G wrong. I don't know, I think I changed the numbers and then I didn't change them when I was doing the answer key, or vice versa. Although it should just be 2 times 10 to the negative 3 because it's 1 sig fig. Is that what we're getting for G? Yeah? If you're not getting that for G, you can call me over because other people are confirming that I'm finally right. Okay, we're good? Excellent. 1.6c, page 14, because we never stop in this class. I'm so sorry, but we are on page 14. 14. Yeah, I goofed up on the answer key. I used the wrong numbers. So the work would look the same just with the numbers from the question, not whatever I wrote there. Yeah. Okay, sometimes we have a reaction that proceeds too quickly to get a consistent initial rate. You'll have the concentrations dropping very quickly, and so the rate will be changing quite quickly. And so you cannot do an initial rate experiment, right? Why can't you do an initial rate experiment? Because the concentration is changing too quickly and we don't get a consistent rate. So we need to measure the rate over time, okay? So we're going to collect some data, and we will end up with one of three possible graphs. We are going to straighten our lines. So you can end up with a 0th order. If you have a 0th order reaction where it does not depend upon the concentration of A, as time goes on, the concentration of A will just decrease linearly. Okay? The rate equation as we know it would be rate times K, because of course A to the 0 would just be 1. The slope, you'll notice that the slope is negative, so the slope is equal to negative K, or K is equal to negative slope. And the y-intercept, of course, if we've got concentration of A on the y-axis, the initial concentration of A will be the y-intercept. Is good? Okay. Don't worry, I'm kind of giving you a summary chart here. If you're like, I don't get it, don't worry, we will delve deeper in, well, probably next class. Okay, so we're just getting an introduction today. Now, let's say you get a curve. When you take concentration of A on the y-axis and T on the x-axis, and you get a curve and you're like, oh, I don't like curves because it's really hard to find the slope of a curve. If you take the natural log of the concentration of A and you plot that versus time, and you get a straight line, if taking the natural log straightens the curve, then you know that it is first order. Okay? And that means that your rate law is rate equals K times A, which would be to the power of 1, of course. And again, the slope will be negative, so K is equal to the negative of the slope. Also, the slope, of course, then would be negative K. The y-intercept would be the net, it would be the, actually this should not say, that little 0 should be on the outside, it would be the ln of the initial concentration of A. Yes? Now, if we have a second order equation and we plotted A, concentration of A versus time, you're going to again end up with a curved graph. Don't like curved graphs, can't find a slope of a curved graph. If you take, and all of this, if you've taken calculus, you could probably figure this out. I haven't taken calculus in over 30 years, so I don't, I'm like, calculus happens if I have a second order reaction and I take 1 over A versus time, that will straighten the curve for me. And like I said, if you have taken calculus, you might be able to sort out how that works. These are actually called the integrated rate laws because you are integrating the thing. But if you don't understand it, remember, I don't understand calculus either. 30 years ago, I might have, but now I don't. Don't use something for 30 years, you lose it. So if you have 1 over A, that's going to be a second order reaction. Your rate law will be, of course, A squared. And you'll notice what kind of a slope do we have here, negative or positive? We have positive, so K is just equal to the slope. Now, if you're like, how am I going to remember that it's 0th order if I get a straight line with A versus T? And how am I going to remember that it's first order if I get a straight line with ln A versus T? And how am I going to remember that it's second order if I get a straight line with 1 over A versus T? Well, guess what? If you get is your sheet yellow? Your yellow sheet your AP equation sheet, and we go to the bottom of the first page, and we find kinetics. Look what we've got here. We'll get into these formats of the reactions, but it goes 0, 1, 2. So 0th order, if you plot A versus time, you'll get a straight line. If it's first order and you plot ln A versus time, you'll get a straight line. If it's second order and you plot 1 over A versus time, you'll get a straight line. So you don't have to memorize that fact. You don't have to be able to do the calculus. You just have to be able to say the first one is 0th, the second one is first order, the third one is second order. We have a whole lot more to go on here. This is just giving you the briefest of introductions. Study for your quiz for tomorrow, and I will see you mañana. If anyone wants an overall review for the unit, I do have one up here. Plus a vocab sheet, so if you want to grab one, it's 1, 2, 3. Ignore the rest of it.
Yeah. Yeah, I got you, bro. I got you. It's your voice of the people. Yeah. Dude, dude, radar just started a whole world.
Whatever that is. I don't find it. I don't know what you type it with. Maybe. Like, how would you type it with like an acid? That would change color? Yeah. And then you just see like exactly what it changes color. This is a happy method of titration. So I don't worry about it too much because I've done a titration to find weight in like enzyme kinetics, an enzyme kinetics lab, and you're like, okay, you've got your lab partner, and you're desperately like, trying to do it really quickly. It's an awful, stressful procedure. Okay. Right? So, you can do it, but it's not the best. Okay. Yeah.
So what she said.
Just because it's awkward and stressful. I remember doing it in a biochem lab with some enzyme kinetics, and like literally you put the things in, and then you're like, okay, perfect.
You have to do it really quickly, right?
Yeah. So it's really stressful, and it's not like acid base or you demonstrate with you won't because you're only in grade 12.
Exactly.
So don't stress about it.
What's up, Ethan?
Okay?